Hello everybody. In this video I would like to show you how to solve this epic integral. I mean, when you look at it, it seems impossible, right? And you would be right to think so, that it is impossible, because I mean, even some simple expressions like sine of x divided by x, there's a theorem that says it's not expressible in elementary functions, right? And even something as simple as the exponent of x squared, the indefinite integral, is not expressible in elementary functions. So why would this complicated seemingly thing would be expressible at all in elementary functions? But it turns out that it is possible. So, and whenever you try to solve it, I mean, if you do something, naive, like something intuitive, whatever you try to do, if you try to integrate it by parts or make some substitutions, you end up messing things up. It becomes more complicated than it even started with. And so here, when you're solving it, you need to have some kind of leap of faith and some insight, and this, this feeling that you want to continue with it, and then a miracle happens. So let me show you what I mean by this. So definitely want to give it a try, then pause the video now and give it a try. Even if you don't succeed, I mean, it's better to pause the video and give it a try, and then keep watching the video, because then after you tried it yourself and then you see the solution, then you've thought about this, and it just has more effect. I mean, you have more appreciation for it. So anyway, I've talked enough, so let's get to business. So let's see what can we do to simplify it. So the thing is that after some long and many failed attempts, right, this is one of the hardest, the integrals probably the hardest I've ever solved in the indefinite ones. So you would try and take the derivative of what's in the denominator. So if we compute the derivative of this, turns out that something nice happened. So well, the derivative was prime. And why would you do something like this? Well, if you would think that, after you've tried to take it by parts, well, maybe if I had here the derivative of what's in the denominator, then, I would be able to compute at least the part of this integral. And it turns out to be that this is the direction, this is the way to do it. And so let's see. So when I take the derivative of the cosine function, it is minus sine of x. And then when I take the derivative of x, it's sine of x. So minus sine plus sine is 0. And then we are left with x times the derivative of sine of x, which is the cosine of x. So the derivative of this, maybe I'll write it more elaborately. So the derivative of the cosine is minus sine of x, and then plus sine of x, it's the derivative of when you take the derivative of x. And here, we're left with x cosine of x. And note how this thing reduces. Yeah, it's nice. So it definitely should give you a hint that you're in the right way. But okay, if we have this expression, I mean, how does it help us? Still maybe not so clear. And let's see. So I said I would want to have the derivative here on top. So what I could do is just force it, right? And I'll show you what I mean by that. So if I write cosine of x divided by x, and here I will multiply it by x cosine of x, and here it's the cosine of x plus x sine of x, all of it squared, dx. Okay, so it's the same expression, but now, as you see, this is the derivative of what's in here. And so maybe we can try to do it by parts. So if this is f, and we'll call it g prime, right, then actually we can compute the indefinite integral of g, right? If we compute the integral of this, that's why we did the hard work. That was the reason for the efforts. So if we look at this, so we have this, right, the integral of this dx, and then we make a simple substitution. We'll substitute t to be cosine of x plus x sine of x, and then as we computed, dt would be x cosine of x dx. So it reduces to the integral of dt over t squared, which is minus 1 over t, which is in our case minus 1 over cosine of x plus x sine of x. Right, so we're definitely making progress. So now if you were to integrate this, take this by parts, then the integral by parts, well, I'm sorry if you do not see, maybe I'll zoom out a little bit, see if I can do it. Yeah, if we zoom out a little bit, then yeah, we can still see the integral here. So the integration by parts will be, it's going to be f, this is g, right? This is g. So it's going to be fg, so it's going to be minus x divided by the cosine of x times what we have here is the cosine of x plus x sine of x. This is this part, and then we need the integral of minus g. Yeah, it's minus, but the g has a minus here, so we may as well replace it by plus integral. So here we have the cosine of x plus x sine of x. And we need to compute the derivative of this, right? But and here's the miracle. So when we compute the derivative of this, what happens is the following. So the derivative of x is just 1, so it's the cosine of x, and here it's the derivative was the quotient rule, right, for the derivative of the quotient. So the derivative of x is 1, and then we have the cosine of x, and here minus, because we have this minus sign here, and here we have x, and the derivative of cosine is minus sine, so actually plus sine of x, and all of it divided by cosine squared of x, right? And then here's the miracle that I promised you. Then if you stick with your attempt, and I mean, if quoting the songs, they could be miracles if you believe, right? So that's the miracle. This is getting reduced, and here we have the integral dx here, and therefore the integral, by the way, in the integral of 1 over the cosine squared of x dx is just tangents of x plus constant. It can be easily verified. Basically, that's an immediate integral, because when you take the derivative of tangent, some trigonometric identities will lead you right away to this. So it's an immediate integral, and yeah, we solved it. I mean, so our answer would be that the integral of x squared divided by cosine of x plus x sine of x, all of it squared, dx, is just, yeah, this is the tangents of x. So it's minus x over cosine of x times the cosine of x. Sorry for the handwriting. I'm trying to write it fast for you. So we have this, and then plus tangents of x plus c, and that's already the answer. And we may want to simplify it, just, you know, for statistical reasons. So let's try and simplify it. So tangents of x is just the cosine of x over the sine of x. So if we'll continue it here, our answer, so it is minus x divided by cosine of x, and here we have cosine of x plus x sine of x. By the way, as I'm writing this, I just wanted to say that lecture notes are available, and in the lecture notes this is written in much detail, so feel free to download them. They're in the description attached to the video. So here we have this plus c, but we see the cosine here is present, so what we need to do is just to extend this fraction by this. So if we proceed here, then we need to compute minus x plus the sine of x times what we have in here, cosine of x plus x sine of x, right, divided by this cosine of x and times this. I won't copy it for now, but the thing is that here we will have sine of x cosine of x, and here we're going to have x sine squared of x. And actually, and here, so the expression that we're going to get is x sine squared of x minus x, which is easily seen to be minus x cosine squared of x. And so here, one cosine would reduce, So I will write it plus c as this way. So once we reduce the cosine, actually the expression that we're going to get is a nice one. So here we reduce the cosine, so it's going to be sine and then sine of x, and minus x cosine of x, and then here at the bottom we're going to have what we had, cosine of x plus x sine of x plus c. Yeah, that's the nicer answer. And yeah, that wasn't easy at all. But actually we can now use this insight to solve another integral which is similar. It's like the brother of this integral, or I would say a joint in some way. But if we look at the derivative of the following expression, if we look at sine of x, basically we flip the sine with the cosine and x goes to minus x. And we take the derivative of this, then something similar to the miracle we've seen before happens. So if we take the derivative of sine, it's just a cosine, and then we take the derivative of x here, it's minus cosine of x, and see how this reduces, and then we have minus x times the derivative of the cosine, which is minus sine, so in total x plus x sine of x, right? And then we, by analogy, could form the following integral: x squared over sine of x minus x cosine of x, all of it squared dx, right? And this integral can be solved by the same method. So if we were to write now here x over the sine of x, and a similar miracle will happen. So it's x sine of x, and here we have sine of x minus x cosine of x dx. So this is squared, of course. So what we see here, that this is the derivative of what's in here. So we'll again take it by parts. So this will be our f, and this is going to be g prime. And then what we'll have, it's fg, but g is going to be, it's minus 1 over this. So we're going to have minus x divided by sine of x, and this is sine of x minus x cosine of x. So we figure that out. And here we're going to have, so minus g, so g is minus 1 over this. So it's actually going to be a plus. It's just absolutely in absolute analogy to what we had. Plus 1 over sine of x minus x cosine of x. And then here we will have to take the derivative of this. So let's make it quick over here. So the derivative of x is 1, and then times the sine of x, and we'll already see that it's gonna be minus x the cosine of x, and here it's gonna be sine squared. So you see it's just the same, and then the miracle happens here. This is getting reduced, and the integral of 1 over sine x squared is minus the cotangents of x. So actually the solution to this integral would be, so the integral of x squared over sine of x minus x cosine of x squared dx. What we get is that it is minus x. I'll try to write it in a beautiful handwriting for you as we're finishing the exercise. Minus x cosine of x, and here there's a sine here as well. I hurried up, and it doesn't look so beautiful as I wanted it to. And here we have minus the cotangents of x plus a constant, of course, and that's another integral that we solved in an analogous way. So anyways, thank you for watching this video, and I hope you liked it. And I hope to keep creating high quality content in the future. So thank you.